Well, we can also like help as we go. Do one person quickly go.
Okay.
Like,
How did you do in your midterms so far? Good? Kind of? Who still has more than 2 midterms to do this week? Oh, okay. Good amount. Okay. Try to make this session not too stressful for you guys. As I mentioned before, the AVL tree, which we're going to cover today, is not part of your midterm, but it's very important. So we're going to have 2 sessions for the AVL tree today and Thursday. They are very important for the final, but they are not covered in the midterms. And you're lucky, usually every single year, we kind of cover them. So you have less material actually for this year in the midterm. But before we start, there was few noticed yesterday in the tutorial. People were still kind of confused about this. When we say O of H, and then we say, okay, worst case is O of N, best case O of log N, correct? People are still kind of a bit confused about that. And that's fine, because the reason is big O, naturally, you're relating it right away to the worst case. So when you see big O of the best case, you get confused because you're used to the omega is the best case. But if you're still confused about that, please go back to the first lecture analysis. I had a few slides explaining this. We said big O, big theta, big omega are what? Are notations. Okay? So they are notations. And we mentioned big O means the upper bound. Big omega means what? The lower bound. Correct? And we actually said for the worst case, you can calculate big O or big omega or big theta. And for the best case, you can calculate big O, big omega. Now, it's not usually, it's more natural to just link the big O right away to the worst case anyway, correct? And the big omega to the best case. Naturally, it's okay to go that way. But they are different. So if you want more details about that, go through these. There's more than one slide. I explain in details, give you examples. For example, I gave you this. If you remember this example, in the best case, what did we have? We have 15. It starts from here. Then we took the worst case, and then we calculated the average case. Here, we're not mentioning at all big O or big omega, right? And then I told you here that best case function is 1, worst case function is n, average case, this is the function of it. For each of these, you can actually calculate omega, big O, big theta. We talked about this. Now, we stopped mentioning these things because we said in this course, we're going to only use big O, okay? But there's another course, I think, where you go into details about the big theta and more things. So don't confuse stuff. It's okay. What I want you to focus on, yes. No, we're not going to have the actual mathematical proofs for that. No. So if I go back here, so that means when you see O of n for the worst case and still big O log n worst case, it's okay. Sometimes we're going to mention, okay, also the theta is going to be log of n for the best case, for example. So don't confuse these things. That's fine. What I want you to focus on here when it comes to what is the difference between O of H and O of N. When we mention the algorithmic notations, the big O, big theta, big omega, what are we measuring here? It's a notation for something, right? So what is it? It's the notation of what? What does it mean? This thing is big O of N. Yeah, and in another way, what does it mean? What are we trying to do here? Measuring what? better word, Riley. And a better word, efficiency, right? And in this course, efficiency is time, complexity. But we want to measure the efficiency. Efficiency of what? Of the algorithm, correct? The efficiency of the algorithm. So when we say O of n here, we don't mean the tree, the H is O of n. No, we mean that inside a tree like this one here, inside this kind of tree, which is a very bad tree, correct? Inside this tree, if I want to do a search, it's going to take me O of n to do it. And this kind of tree, this one here, the balanced one or perfect one, if I want to do a search or insert or delete, it's going to cost me O of n. That's how I can measure. So I'm measuring what? The operations, the search, the insert, the efficiency of these algorithms. What we meant by O of h time is that if I want to give a general case, if I'm asking you these methods, find, insert, remove, takes what? You're going to say takes O of h time. Why? Because h is the one that's going to define n or log n. In this case, what is the height? Is n. In this case, what is the height? Log of n. So that's what we mean by O of h. H is just, we're saying that to be able to know the efficiency of the search, find, and insert, it's linked to the height of the tree that you're working on. So that's what it means. So in conclusion, you can still say, in the worst case, BST will be what? O of n. In the best case, O of log n. Okay? Good? Okay, very good. So now we can move to our, yes.
When you say that BST is best case and best case log n and worst case, and you mean that like the structure of the binary search, you mean by the height, right? Because like
It's linked to the height, yeah, proportional with the height.
it's like if, for example, if you were going to say like finding an element in a binary search tree, like that's a different than saying like the big O of finding an element in a binary search tree is different than the big O of the height of the binary search tree. Because then, like, for example, if you're looking for the worst case, it would be n, but in the best case, it'd be constant, right? For the search part.
Yes, exactly.
Or is the height? We're talking about the height part in the course, but we haven't talked about the part.
Exactly. So here, when we say the best case, that means the best case of the structure of this tree is going to be big O of log n. Very good, Anthony. So guys, again, to explain it better, in this case here, this is the best case, right? What would be the big O of this? Log of n. But the big omega of this, for example, or whatever, like it's going to be here at the root. It's 1. Maybe it's better now. It was not clear before. Okay. Okay, so let's move to the AVL. Yes, Abid. Yeah.
So for this worst case, we're saying that the height is n, right? So for this same tree, if we build it so that it's symmetrically, the height will change to log n, or is it most mistake?
If you have this tree and you start filling on the left and you end up with a balanced tree, that the height will change.
How's the height going to change where we have the same elements, the same nodes?
It's not going to change if you have the same nodes. You're asking me if we add to this. If I add more nodes, then it's going to change, of course, because you're adding more nodes. That means you're playing with the height. But if you're not adding anything, that's how it looks like. It's like this. It doesn't change if you're not adding any nodes. Why would it change? I'm not sure if I answered your question. That's what you meant?
I meant if it is, in this case, it is of n.
In this one here.
Yes.
Yes.
So if we filled it,
What do you mean by fill it? But this it's filled. That's why it looks like this.
okay.
Do you know what I mean? So This is not an empty one. For this sake, we don't have keys inside them. But this is filled one. That means we answered numbers, first number, second number, third number, fourth number, fifth number. We ended up with this. But we don't have the keys here because this is just an example. Yeah? You had a question?
You answered.
Perfect. Yeah. So this is from the book, guys. So it's just a general case. That's how the book put these. But you're going to imagine that you have actually keys inside these. Okay. Okay. Very good. So we're going to do another recap now so we can be on the same page so we don't lose the bigger picture, right? So we're going to use the same exact story that we used last time. So we're going to continue this story. Do you remember last time we had a bag of what? Of data structures that we built so far that we were able to use, correct? And then we asked, where's Anthony? We asked Anthony and Zach to use this bag to solve a real world problem. Now, you continued with this course, so you have more data structures to add. So we're going to just check what we have so far. We said we're helping them to build their software solution company. And then what do we have? We started with array linked list. And then we added these, but priority queue, binary tree, and then we now added the maps, correct? The maps is using binary search tree. Very good. So now inside this bag is bigger now. What do we have? Maps added to this bag. So someone from you decided, you know what? I got the ultimate ADT, the ultimate data structure BST. That's the best one. I'm going to drop this class and go and start my own startup company. I don't need to know other type of data structures. Who's going to be this person? You want to? Who wants to? You want Noel? Basil? Why you're scared? Are you mad because we didn't pay Anthony and Zach last time? It's okay. You're still students. So who wants to try to now do the same thing that we did last time? We're going to ask a real world question, for example. James, you want to try it? Okay, so I'll give you a mic and then we can think together.
Okay.
Oh, so let's start. So you learned about the binary search tree. Okay, so I'm a client. I'm asking you, you know what? I want you to build me a software that can store inputs, but what I really need is an efficient software that make it easy for me to search. It's like a directory. I want to search. So what are you going to ask me?
Will there be a constant set of data or will it be a dynamic set?
Let's say there is a constant set of data. Yes. So I know exactly. I have, for example, no, it's going to be dynamic. So you're going to start with, let's say, 100 entries, but it's going to add. Now, what is the best thing that you have so far from this bag? Search.
The best thing to search would be
Let's make it easier here. Last time we did priority queue
we would use
or a binary search tree.
we would use a binary tree.
Okay. Why, guys, we're going to use the binary search tree? Because last time we had specific things we wanted to use stuff based on priority. So we use priority. Now I want to search. I don't have a priority. I want to search in my data, collection of data. What's going to happen is that you're going to use a binary search tree, correct? So I'm giving you my entry of data, which are from 1 till 20. Okay?
Okay.
So let's do it together if you want. You can do it here.
Okay.
So let's say I'm giving you this one from 1 to 20. So this is my entry. Let's say from 1 to 10. Okay. So how are you going to use the binary search tree to system? Very good, let's stop here, it's okay. Okay, so. In this case, my entry, I gave you these entries. What's the problem here, Jane?
It's a complexity of OM.
Exactly, it's not efficient enough. So here, James start regretting dropping the class and starting his stuff, correct? Maybe you're going to ask me things. What do you think I can have a solution? How can we fix this entry? Because we noticed that because they are ordered, right? That's why this is happening. If you want, you can get help from your employees. So anyone want to help James also? The question is, James noticed that the main problem here using a binary search tree is what? These entries that I'm giving him are ordered. So because they are ordered, he's having this problem. Riley.
Randomize the array so that it's now out of order and it's easier, or you can start in the middle and then do some kind of thing where you get to the middle of the next part and then the middle of the next part, and that way you can be putting something on the left and the right every time.
If you want, James, thank you. You can sit.
Thank you.
So, one of the employees of the company suggested what? Let's randomize these numbers. So I'm the client, I gave you these 20 entries, and then we decided to randomize them. So if you shuffle these to a maybe randomized function, they're going to be randomized, maybe it's not both. Another employee wants to argue with Riley. Yes.
I don't understand why randomizing would help the situation.
Why? Because if I'm giving you 1, 2, 3, 4, and you want to answer them in order like this, you answer 1, you're going to answer 2, 3, 4, you're going to have a scoot. This is the worst case, so you're going to end up with O of n. That's not efficient. To be efficient is going to be O of log n. So he's saying if we randomize it, it's going to end up, for example, like this: 5, 8, 2, or something like that. Then it's going to be maybe more. You cannot reply to yourself.
Can I argue against myself?
Let's see someone else. By the way, you don't have to give a solution. Maybe you can ask something from me. Then remember, this practice is that you're in a company, right? So maybe you can ask something for the client. Yes.
When we randomize it, wouldn't that be like O of n?
So you're talking with Riley. Ask him.
If you randomize.
Don't fight. So she's telling Riley that randomizing them may be costing us of n before even starting to implement the binary search tree. Riley is replying.
I guess it matters, it depends on if the startup cost matters, right? Like, we had different scenarios where you want the search to be effective, not necessarily the creation. But yeah, O of n is pretty bad.
Okay. Well, you admit that maybe there's a problem.
Like, the structure is optimized, but the way to create it is not optimized.
Exactly. You want to add something? Yes.
I mean, like right now you have the sorted sequence, and you like start with 5 and then you have 3 and then 8 on the sides. And you can just do like binary search on the sorted sequence. And that's how you pick the order.
So you want to actually do what? Because here, the idea is that you want to insert them, because if you want to go to the, because you have to think about that, not just a fixed thing, having sorted things over. So this is the first entry. So we want to have a solution that will work dynamically. Anyone else had their hand raised? No one's asking anything from the client. One of the questions may be what? Why you're even giving me sorted data? The client's going to tell you, because I'm not going to put the effort to shuffle every time I need to what? Enter that for. I need something easy. James?
Okay, I know this might be a bit backwards, but would it be good to use array list in this? Because it's already.
Array list will still have the problem of searching, because you need to search, it's going to be open. That's the problem. Okay. So now you want to add something, Riley?
I really like the idea of going in the middle of the thing, so every time we add something, we cut it in half, take the middle part, add it to the tree, and then cut this half in half, take the middle part, add it to the tree, cut the other half in half.
Yes, it's not going to be as efficient. If you do the whole one, it's not going to be as efficient. Now, let me give you something that's going to be dynamic. Why? Because you're saying this. Let me give you an example why this may not work. Think about now from an actual real world problem. My software that I want you to create is what? I have an e-commerce website, like I'm selling things online, and what's happening? I need to store things. The key is the timestamp. So what time this operation, what time this, I sold this, what time? So what is the key? Is a time. So each time like something is sold, what is the key sent is the time. So after that, the time is always going to be what? Sequential, right? Like, it's not like I'm giving you now, when you think about it, forget about this, you sorted it. No, you can't always divide, because if I'm adding, the next one is going to be 11, the next one is going to be 12, the next one is going to be 13. So you have nothing to divide. This will only solve it in the first entry. But if you have something, you want to build the software, and the key is based on time. So the next entry will always be the sequential one. You see now why it's harder? It's getting harder and harder now if you want to actually just use a binary search tree. You're not going to be able to just solve it. Yes, you need to watch the lecture today and then you start your own company. So what's going to happen is that we need to find a method that's going to solve this issue by what? By having it will balance itself, for example. Each time I give an entry, I don't need to do anything, it will self-balance. Looks like science fiction, but we're going to actually prove it. Let's go back to the recap and why we're looking at this. So we do the recap is what did we start after adding to our library the ADT that allows us to access the min and max keys to implement the waiting list, emergency room, whatever. We decided that we want to do what? We started searching for an ADT to solve the problem where I need to be able to access any key in my data. That's why we came up with the idea, the ADT of the map. Now the binary search tree is what is used by the map ADT. Why? Remember, remind me why, because when we explain map, were we able to implement it without the binary search tree? Who says yes, who says no? Were we able to implement the map ADT? What is the map ADT? Is access any key in my data. Be able to search something, I have a data, and I need to access any key in it. Were we able to implement the map ADT by something other than the binary search tree? Yes. Or the binary tree techniques? What did we try to implement? No? Okay, let me refresh your memory. So this is the track that you had. What did we start before moving to this? Before moving to the binary tree, which one we used actually to implement the map? Why these recaps are important, guys? So if I am explaining something to you that you don't even know why we're even explaining it and why it's beneficial. No. No. We explained it last week, guys. No. We used to make maps. What did we use? Now you're scaring me. Raise your voice. What is the sequence he's asking you? Yeah. What is the sequence that we used? No, it's not this. What is the sequence, guys? What type of sequence did we use? Oh, Sandra. Yes, but technically, what did we say? We actually tried it with ordered sequence, unordered sequence, and then we proved that it's not going to work. That's why it's going to work. It's not going to be efficient. We're going to get stuck with O of n. That's why we jumped to the binary tree. Okay, so again, guys, I need you to understand these things. The MAP ADT is an ADT, it's an abstract data type that allows me to access any key in my data. That's the idea. Now I want to implement it. We started by using a sequence because we had it. And we said, okay, it works. I can build this map, but my problem is I'm going to end up with O of n. Then we said, okay, binary search tree is going to be better. Why? Because a tree can have a best case of log n, correct? And that's where we did the binary search tree and we started doing. Now, we said the ordered and unordered sequence is going to cost me O of n. So that's why we started looking for a better way to implement our map, and then we did what? We found that a better way to implement the map is the search trees. Okay, what type of search tree we covered so far? The binary search tree. We started implementing the binary search tree, which is based on the binary tree data structure that we saw earlier, and we noticed something, that it's going to be O of height. And when the height is with the best case, when we have the best structured tree, we're going to end up with O of log n. What is the big issue that we faced? In the worst case, we're going to go back to O of n. And that's why we're actually covering and studying this lecture. Okay? Because if you don't follow this, you're going to think that the topics are not related to each other and you're not going to get bored. Now let's talk about the AVL tree. So what is the idea of an AVL tree? We said the height of an AVL tree, AVL trees are balanced, but they are self-balanced. I don't need to interfere each time I add something. An AVL tree is a binary search tree such that for every internal node V of T, the heights of the trees rooted at the children of V at most one. So what do we mean by this? First, search trees, guys, don't have to always be binary. We're going to see the 2-4 trees, it's not binary. Okay? But AVL is binary. Binary search tree is binary. Oh. Now, what is the difference? This is the difference. Going to be at most by 1. So if I have something like this, guys, the difference between these, any node is going to be only by 1. I'm going to explain it more. Now, the thing that I want you to pay attention, in the past, what is the height of this? How did we do the height before this? It's 4, why it's 4? We're going to start with what? Yes. You said 4, the height? Yeah. Why? We're going to start from here. 0, 1, 2, 3, and then we can say 4 with the dummy leaves. Okay? Because usually binary search tree, we're going to do the binary. Now in the AVL tree, I want you to always do the opposite. The height is going to be here at the top, not at the bottom. Why? Because I want to put the height next to each node. Because I want to put the height next to each node. What's going to happen? So what is the height of this? 0, 1, 2, 3, 4. What is the height of this one? 0, 1, 2. This one, 0, 1. So that's how it's going to be. Next to each one, each node, you're going to have the height because we're going to use them to calculate. The most important thing is something called the balancing factor. So this is how you're going to self-balance this tree. What is the balancing factor? It's the height of the right side minus the height of the left side. Okay? And if my balancing factor is -1, 0, or 1, that means this is balanced. This tree is balanced, that's good. Whenever it's -2 or 2 or 3 or whatever, that means I need to rebalance it. It's going to be doing this self-rebalancing. Okay, so you're going to code it in a way that each time it's not these 3 values, it's going to self-rebalance. Let's give an example. If I want to calculate the balancing factor of C. Who wants to do it? Yes.
1 minus 2.
1 minus 2. -1. Is this -1 here? That's good, very good. That means this is balanced, for example. Yeah, I'm good. Now I want to do B. Riley.
So I would do right minus left,
1 minus 1,
right one, yeah,
0.
0, so it's.
It's here, very good. A. Fida,
P minus 2.
3 minus 2. Now, why I'm doing this? When you do the balancing factor, it's not that you don't use the balancing factor minus the balancing factor. You use the height minus the height. So that's what you need to pay attention. That means -1, sorry, 3 minus 2, 1. So we look here. Going to be 1, and then that's 1, correct? And then the same thing for everything. So that's how I know this is balanced, because all of the nodes have between -1 and 1. Very good. In the binary search tree, we had a problem when this is what is O of n, because it's good. Now someone may come and tell me, but we already solved this issue. Through what? Through a heap, because it uses complete binary tree. What is a complete binary tree? Left shell, and what is the height of the complete binary tree? Log of n. So I already solved this using complete binary tree, using heaps. Who wants to answer this? Who wants to reply to this claim? It's very dangerous claim that someone is saying. Let me hear more. Why? No, the problem is not solved using a heap, even though the height is log of n. Why? You see how much time, guys, we're spending on just pausing and letting you think? Because that's the majority of the time what we're going to do when you're programmers. Critical thinking before coding. If they want to hire the coder, they want to hire technicians. They go to a college 1 year, that's it. You have 1 year of certificate, you know how to code. And they will just be given you tasks, go for these. You will pay them much less than you. So you need to learn how to think more than coding. So why, if I ask you in an interview, you're going to a job interview, guys, I'm telling you, the problem here is often, but I already solved it with a heap. Why do I need an AVL? What's your answer? Very good. Heaps is what, guys? We said heap is made as a min or max. So you're going to always remove from the min or the max. It's based on a priority. You're always keeping the priority in the root, which is the first index. So you're just using this O of 1. It's very good for you, but searching is not very efficient in a heap. So we need something that has a better capability to search, because our ADT now is a map, not a priority queue. Okay, now we're going to cover a bit of math. I'm going to go through it. If it's still not clicking, I'm going to post a video from previous year where I explained actually the math in detail. You can watch it again if it's not clear. Okay. So here, guys, in a perfect binary tree, we said it's going to be n equal to the power of h plus 1 minus 1. So h is log of n. The problem of not being able to use a perfect binary tree, so we're going to use just a balanced tree as well, because perfect is not practical, it's not realistic. Rarely you're going to have a perfect binary tree, okay? So the AVL focuses on something, which is the minimum number of nodes of an AVL tree of height h. So this, when you see this NH, that means how many nodes, what is the minimum number of nodes I can put with the height of h. So I'll give you an example. In this case here, what is my height? 1. What is the minimum number I can put? 1, anyway. Now here, if I want to have a tree with height 2, what is the minimum number I can put? I cannot put 1, I have to put 2. So these are fixed. Now my problem, or like what I need to prove mathematically to end up with log of n, is anything whenever I have a 3 nodes and up. So these are very clear. You don't have any alternative when you have a height of 1 or height of 2. But if I have a height of 3, what's going to happen? So this is height of 3. So 3 nodes. 4 nodes, I'm still height of 3. 5 nodes. You see, there is more than one answer when it comes to height of 3, but these are the same number of nodes. Okay. Now, for n greater or equal than 3, an AVL tree of height h contains the root node, as we said, one AVL subtree of height h minus 1h. The AVL tree will always look like this, guys. The balance, the AVL tree, because it's balanced, it's always going to look like h minus 1 and then h minus 2. Or the flipping it, or like on the left h minus 1, on the right h minus 2, because it needs to only differ by 1. Yeah.
The AVL tree, will both sides never have the same height?
If they have the same height, it's going to be a perfect tree. So it's already solved for us. We already proved that the perfect tree is log of n, so that's easy for us. Now, we want to prove that even if I don't have a perfect tree, is it still log of n or no? Because it's not perfect. So that's what I'm trying to prove. It's similar than when we proved a complete binary tree is log of n. We actually had to do a few calculations to prove that even a complete binary tree, which is not perfect, can still be of log n. The height can be log of n, I mean. So now, what is the total number? So what is the number nh? It's going to be 1, which is the root, correct? Plus the number of nodes here, plus the number of nodes here. Correct so far? Very good. Now, can I say that this is greater than nh minus 2? Of course, if you look at it, this one is of course greater than this one. That means, but I can say, guys, I can just say, because I'm going to replace this by this one. So I can say 1 plus nh minus 2 plus nh minus 2, and then I'll say greater here. Okay, so that's how we go with the math logic. So what would I end up with, guys? nh is greater than 2nh minus 2, correct? So I'm going to take this with me to the next slide. Now I prove this. But then also, okay, I can still say that nh minus 2 is greater than what? 2nh minus 4. How can I say that? I'm just replacing h here by h minus 2, and I have minus 2 here, so it's h minus 4, okay? So simple calculations. Now what's going to happen in this case? I will replace this by this, so I'm going to replace it here. I'm going to end up with 2 times 2nh minus 4, which is this. Okay, again, if you want it to be slower, you can watch the video slowly, you can catch it. Let's do it again with another example. nh is greater than 4nh minus 4. The same thing I can say nh minus 4 is greater than 2h minus 6. Now be careful here. Why it's not h minus 8? Because I'm not replacing this h minus 4 here. I'm not saying h minus 4 minus 4. I'm replacing this always with the original one. The original one, it's h minus 2. So I'm saying h minus 4 minus 2, that's h minus 6. I'll end up with this one here. Okay? Now, if you continue doing this, you're going to notice a pattern. What is the pattern? Here, this 2, 4, 8 is 2 to the power of I. And then here, we're going to have 2 times I. So here, if you have 2 to the power of 2, you'll have 2 times 2. 2 to the power of 3, you have 2 times 3. Okay? So this is what I concluded so far. Now, I'm going to also add to it, I already know that n1 equal 1 and n2 equal 2. We know them from the first slide. Why? Because this one is just a root, and this one is what it can only be 2. Correct? Okay. So what can I say? If this is my general case, guys, and I know that n2 is equal to, so I'm going to take what's inside n, because I have n here. So I'm going to say h, this is one, I can either say h minus 2i equal 1, or h minus 2i equal 2. So I'm going to take this, h minus 2i equal 2, okay? And I want to get what? I want to get I. Simple math. 2 minus h. And then I equal what? H over 2 minus 1. Correct? Now why I'm saying seal, not floor? Why even I'm saying seal? Because what if you have an odd number? What if you have 13? So 13 over 2 is what? So there is a decimal. So we're saying that always take the seal. That means take the higher number. Okay, that's what we mean. Now I have my I. What am I going to do? I'm just going to replace this function with the I. So look, I replaced here the I by this one, and here the H minus I, because I've said when it is n equal 2, it's going to be 2. So this is 2, and then you just continue doing it. We're going to end up with, if I do log here and log there, we're going to end up with log n greater than h2, and then h greater less than 2 log n, which is O of log n. So here I just that even if I keep the balance in this way, where it only differs with 1, it's going to still be O of log n. Now again, for you, in your daily life, you only need to know what an AVL is O of log n. But it's good to know the math behind it. Why? Again, you can take a look at the video that I'm going to post. Now let's jump actually to checking how do we insert. So do you remember when we said usually when we insert in the binary search tree is strict, there is no balancing for it, maybe end up like this. So now we're going to check when are we going to balance. So now this balancing factor here is 0. I added something on the left, I ended up with -1. Okay? If I add something on the right, I added with +1. Do I need to rebalance with these? No. In this case, I don't need to rebalance. That's fine. If I already have it +1, I add something on the left. Do I need to rebalance? On the left? No. Going to be 0. On the right, +2. I need it to always be -1, 0 or 1. +2, that's a problem. I need to rebalance. So when you're coding the AVL tree, you're going to have these conditions. Whenever the balancing factor is not one of these, then trigger the rebalancing. In this case, the same thing. I have -1. So if I add something to the left, I'm going to rebalance to the right node. So let's see how are we going to do this. In this example, what we're going to do is, whenever you add something, let's say I added something here. Start calculating the balancing factor here, here, and then here. I arrive to the first node that it's not balanced. I'm going to give it Z, Y, X. So this is my first node that's not balanced. So let's assume the balancing factor here is 1, here it's 0, and then, for example, here it's 2. Yeah? That means this is my first one, which is unbalanced. I'm going to name it Z, then the child Y, and then X. Okay? We're going to see an actual example. Don't worry about it. The second step, this is my first step. The second step, I need to do the 4 substitutes. After I have my Z, Y, X here, what's going to happen now? I will start from left to right. So anything here connected to this is called T1. Anything here, T2, T3, T4. Let's get that function. I'm going to see an actual example. My third step now. Now here I just decided that Z, Y, X, and all. I still need to rebalance. How am I going to rebalance? Based on what? You remember in the binary search tree, we said if you want to delete something or whatever, you're going to choose the next one based on what? Which type of traversal? Yes? In order. In order. In order, because it's going to be ascending. It's going to be ascending order. The same thing here. First thing you're going to do in step 3, you're going to figure out the N order. And then based on the N order, you're going to label your Y, your Z, Y, X. For example, this one is the first one, second one, third one when it comes to the N order. So I'm going to be A, B, C. So the main mistake that students do usually is they will do the ABC always the same, like from top to bottom or from bottom. No, it's not always X equal A. It's not always Z equal A. Depending on the in order. We're going to see a lot of examples, so don't worry about it. Now we're just explaining the concepts. Then the next step, if I say this is my B, this is my A, this is my Z, that's how we're going to change it. The B is going to be in the middle, and then A left, C left, and then T1, T2, T3, T4. We're going to be your revised. So let's see an actual example. I want to insert 54. How am I, why did the 54 end up here? Why? Yeah. Exactly. Very good. You see, we need to connect things to each other. AVL is a type of a binary search tree. How do I insert in a binary search tree? Is it from left to right? No, it's binary search tree. 54 is greater than 44. I go here. It's less than 78, greater than 50, less than 60. So I answered it here. Good. Very good. My next step is what? This is height 0, height 0. What is the balancing factor here? That's 0. And then this is the height equal 1. Now height equals 0 here, correct? What is the balancing factor of 62? 0 minus 1, that's minus 1. What is the height of 62? 0, 1, 2. Okay, what is the height? 1, what is the height here? So that's 1, 2, that's 3. Okay, now height here is 1. So what is the balancing factor for 50? 1. Why? Because I have height 2 minus 1, that's 1 as a balancing factor, correct? All of them are good so far. Okay, let's go here. What is the balancing factor of 78? Why minus 2? Right minus left. 1 minus 3 minus 2. That means I found my first unbalanced node. So it's going to be labeled Z. Okay? Now I do Z and I trace it back to the node that I inserted. That's why I don't go to the 88. I need to go back to the same route that I inserted. That's why online or in the book or sometimes they're going to tell you, no, we're going to start from here, X, Y, Z. When you're calculating it on paper, it's usually easier for you if you start from here, Z, Y, X, okay? But from a code perspective, you may have to start from X, Y, Z, okay? Now I know my Z, Y, X. So let me Z, Y, and then X. What is the next step? What's the next step, guys? Next step, we said we have 2 steps still to find the T1, T2, T3, T4, and then also we need to do the ABC. So let's start with the ABC. How can I get the ABC here? Which one is the A, which one the B on this?
By order?
By in order. Very easy. This is a practice for the midterm. That's it. Practice it with me. How can I know the in order here? Because I need to choose the ABC based on the in order. So which one is the, what is the in order of this tree? Yeah. And also, just a hint, usually, if you have the keys already, you can just sort them from what? In an ascending order. You don't even have to do the left, center, right. That means 48, then 50, then 54, right? So it's going to be ascending order anyway. That means what? I'm going to have 44, 48, 50, 54, correct, guys? 62, 78, and then 88. Is this the in order? Yes. So the next step, I'm going to say, what is my Z? Z is here. Z is 58, that's Z. What is Y? Y is 50, that's Y. What is X 62. You know why I'm doing these baby steps with you guys? Because in the midterm, we may give you like that big of AVL tree. You cannot just look at it and do it easily. You have to actually do these steps to understand them and then do it properly. In this case, what is the order of ABs? A, B, C. It's always like that, okay, in order. That means my Y is A, my X is B, and then my Z is C. Good? Okay. My next step now is what? I want to find the T1, T2, T3, T4. These are just the one connected to the ABC or to the XYZ. What is the first thing on the left connected to Y? What is the first node or bunch of nodes connected to Y on the left? 48. You see? What is the next one connected to one of the Y, X, Z from left to right? 54. The next one, this one here, the empty. The empty, the time node is part. And then at the end, this is the fourth one. Okay, what is the next step now? Because I did all of this to be able to rebalance. How do I rebalance, guys? We said we're going to rebalance based on the ABC. We need to have the B, A, C, and then T1, T2, T3, T4, correct? So what's going to happen? This. Just put the B here, which is 62 DC, and then I put the 50 here, 78 here, and then T1, T2, T3, T4. That's it, it's balanced again. How do you check in the exam that it's balanced again? You just perform check it like a binary search tree. Is everything here less? Is everything here greater? All of these kind of things. You check the balancing factor of everything. And we check the balancing factor because these are the height and the balancing factor, then you want to make sure that this is balanced. Now, why are we doing these steps very carefully, step by step, all of these things? You may look at it, you may say, maybe I can just jump right away to this thing. Because again, this is what? We're going to transform this in actual code. We need to make sure in this code, we don't use like a loop for no reason and we end up with O of n. We want to do these steps this way because when you're coding it, you're going to make sure that you're not looping for no reason. You're just using primitive operations, for example, and stuff like that. We're going to actually stop here. And then we're going to continue with the removal next on Thursday. And we give you 2 or 3 examples from midterm finals. So don't worry about it. I just want you to have the idea. Good. I hope that's just